Welcome to a Hopper internals video. Hopper is a curly brace and semicolon language. If you want to know more about the sort of high-level info about the language and the platform, I have a lot of videos on my playlist that you can watch. This is an internals video that assumes that you're already a bit familiar with the subject. What I want to talk about in this video is the switch statement and the recent implementation of that. The nice thing about Hopper is that it's all written in Hopper, and the source code exists and is available for all of it. So this editor is written in Hopper, the optimizer is written in Hopper. So here's the source code in front of us for the instructions under code generation, if you look on the top right at the path. So instructions in Hopper have historically been either 1 byte wide, like this Boolean not instruction. It just takes something from the top of the stack, knots it, and puts it back. It's a stack-based virtual machine, much like Java. So that's why the opcodes are the way they are. And these jump instructions are either jump Bs or jump Ws, and the W means it has a signed integer offset, so it has a 2 byte operand, whereas these ones have a single byte operand, the signed byte offset for the jumps. So up till quite recently, it's been quite hard to do anything that doesn't have a 1, 2, or 3 byte instruction. And I wanted to do that to do this kind of implementation of the switch statement. So I came up with these 2 new instructions right at the end of the list. Nice names, JIXB and JIXW. So the one has they're both for switch statements, and they have either 1 byte offsets or 2 byte offsets in the switch statement. So if it's a small switch statement like this little one right in front of us here, this is probably using the 1 byte offset, whereas a bigger one with more code will use the 2 byte one. Anyway, I compiled and we generated the disassembly. So let's switch to go and have a look at the disassembly. Right, so this is it's been modified, it's loaded again. This is the disassembly of that program that we've just looked at. So let's search for a JIX. Let's put a space in front of it so we don't see it in the comments. There we go. So this is a JIXW. So quite a big one. So let's have a look at a smaller one first. Oh, this one's tiny. So this is also a JIXW. So it has so 2 byte offsets, as you can see there, but it only has 3 of them. So the way it works is the first 2 operands of the instruction are the range of the case switch case. So I might have added that this only works for 1 byte switch cases. For integer switch cases, or Hopper also can switch based on a string. It still uses the old method of the stringer jumps. Anyway, so this table here is what makes switching really fast. It's a single instruction now. It'll pop off the stack a byte and then look it up in the table. If it's not within the range of the table, in this case the table only has a 0, a 1, and a 2, then it'll fall through to the default, which is just after here, and this one doesn't have a default. Let's go have a look at this in the source code. So Hopper code line 890. Let's go to that file, and I'm going to use this sample. This is the Gibble sample quite a lot in these internal videos as a use case. So there we're at the end of our switch statement. So scrolling up, the switch statement does indeed have 3 cases: a 0 case, a 1 case, and a 2 case. So I forgot to switch. There we go. Sorry about that. So the switch has 3 cases: a 0, a 1, and a 2. And that's why that table only had 3 entries in it. So small switch, tiny table for switching. And something you'll notice about Hopper switch cases is there's no break over here. Break only means one thing in Hopper. It means break out of the current loop. It doesn't have 2 meanings like in other curly brace languages. And switch cases never fall through to the subsequent one by design. So you never end up with bugs related to that, and you never have to put in this extra little piece of safety at the end of your switch. And the thing you give up is the very rare case where you might actually want to fall through on purpose, and I don't care. So let's go look at a bigger one. And it can be a very efficient way of writing certain kinds of code. So let's look at, let's switch back. I keep forgetting to switch. This is not my strong point, making videos. So this one's huge. So it has a range starting again from 0 and going all the way up to hex 69. So that's what these are, offsets. And then it has a default as well, which is what this jump below is here. So this jump below, we should see where that takes us. It takes us back up to something that starts with byte equals byte. It's sort of switch of the instructions. So it takes us back to line 862 in the instructions.hopper. Let's go have a look at it. And I will try to remember to switch back. There we go. What did I say? 862. Let's go have a look. We go to hopper, instructions, 862. And it is indeed the default. At the end of a very large switch statement, so toString of instructions was implemented with a switch statement, which seems insane until you see that it's one instruction in the VM, and it's super efficient. Anyway, that's my first video, first internal on showing what one of the implementations of one of these looks like. I should have queued up. I guess I can still do that. I should have queued up what the assembler of that looks like, just out of interest, for the 6502. I can get there pretty quickly. Let's do that. And once I've got it open, I'll switch. Okay. Switching back. This is what the 6502 assembler looks like for the table, just out of interest. So yeah, there's a JIXW instruction. Comes in, checks the range. If it's not in the range, it goes straight to the default, falls through to the default. And the default case is anything that's not in the table, or anything that is 0 in the table. So the table's contiguous from the smallest to the biggest of the switch cases. And then if it hits one, then it has to jump to use the table, and then this is how it calculates the PC, the program counter address from the index, and then just jumps there. So a lot less, especially since these are 6502 instructions rather than hopper jump instructions, jumping through a jump chain down, that long list of cases. This is a lot faster and also a lot smaller. So I did it for both reasons, to optimize both size and speed. And we're back in hopper. Yeah. So it was to optimize both size and speed for the basic interpreter. You can give us some feedback if this is not that interesting, or what would be more interesting, or what I missed, what I need to talk about. Thank you.